All right, let's take a look at exercise 13.1. So the change in molar entropy of an ideal gas is given by the following equation, where T1 and T2 are the initial and final temperature, respectively. P1 and P2 are the initial and final pressure, respectively. R is the molar gas constant, where here's the value in SI units, and Cp is the ideal gas heat capacity, which is governed by the following equation, where T is in units of Kelvin, and then Cp divided by R is dimensionless, right? So I take this, multiply by R, get heat capacity in my favorite units. Okay, great. So problem one, we're told that methane is available at T1, so we're given T1 and P1, and it's compressed 2. We're given T2 and P2, and asked to compute delta S. So if I look at our equation here, okay, so actually this part of it, we're given T1 and T2, so that means I can evaluate my definite integral, and then I know P2 and P1, so I can calculate this directly. So problem one then essentially reduces to just directly calculating this, which involves performing an integration of the first term. Great. Let's go over to MATLAB and let's get this animal set up. Okay, so I'm going to start by creating a new script. Um, I'll just leave it as a script for now, but let me start by collecting parameters. Okay, so I'm going to start by collecting parameters from the problem. Okay, and so let me have temperature T1 and T2 in Kelvin. So T1 is 300 Kelvin. Okay, I'm going to put them on the same line here. And T2 is 500 Kelvin. And I'll say pressure P, and let me, yeah, we can call it P1 and P2 in, I believe it's given in bars. And when it comes to pressure, we just have a ratio of pressures. So as long as they're absolute pressures, it doesn't matter what the units are. So I'll just keep them in bars. And so I'll say P1 is 1 and P2 is 100. Okay, great. Let me get my molar gas constant in joules per mole. So in SI units, and so R was 8.314. Let me get my constants for my heat capacity. So we have A naught through A4. And then I'll say I'm going to multiply by R to get constants in units of joules per mole Kelvin. Okay. And so as long as, so I'll get this in joules per mole Kelvin. This is already in Kelvin, right? So this then will be in units of joules per mole. Great. Well, actually, this is joules per mole Kelvin. Okay, but then this dt, those units actually cancel those units. So this is joules per mole Kelvin. Right, R here is going to be joules per mole Kelvin, and this is dimensionless. Okay, so everything works out. Okay, so let me get my constants. So A naught, and let me just type them. Then I'll multiply by R. A naught's 4.568. A1 negative 8.975. Negative 8.975 times 10 to the negative 3. A2 is 3.631. That's times 10 to the negative 5. A3 is negative 3.407. Negative 3.407 times 10 to the negative 8. And a 4 is equal to 1.091. And that's e to the negative 11. Okay. Then it said it's going to take all of these, and I'm going to go ahead and I'm going to multiply by r, so that I don't forget and leave them in dimensionless form. Okay, great. All right, and that should be everything I need. So let me start. So let me say, so first let's compute actually I'm going to calculate the pressure term first. Okay, why? Because the pressure term is easy. So let me call it something like P term. And my P term here is just negative R times log of P2 divided by 1. So it's just minus R times log of P2 divided by P1. Okay, perfect. Okay. Now the temperature term. So first, a function for the term to be integrated. Okay. And so what I mean by that is we're going to have to calculate the integral of Cp divided by T. So to evaluate that integral numerically, okay, I'm going to use the integrate function or integral function, but I still need to have a function for the function to be integrated. Okay, and so I'll just create an anonymous function, and so I'll call it CPT. Okay, and so this is going to be a function of t, and so CP divided by t is nothing more than CP divided by t. Okay, all right. So what is CP? Okay, I've already multiplied my constants through by r, so it's just going to be this, and then I'll divide by t. So it's going to be a naught plus a1 times t plus a2 times t squared plus a3 times t cubed plus a4 times t to the 4. Okay, did I get that right? Okay, good. That's that first term. So I'm going to make all these element-wise operations. Okay, great. And then I need to divide by t. I can either go and just start manually dividing terms by t and canceling, or I can just take the whole term in parentheses and divide by t. Right? It's exactly the same. So do whatever would cause you to make the least amount of mistakes. So here I've created an anonymous function. So this is essentially a function for Cp divided by t. Okay. Now we can integrate. Okay, so I'll call this my t term is going to be equal to, so now I have the integral of Cp over t. That's the anonymous function I just created. And I'm going to integrate from t1 to t2. Okay, so integral, okay, Cp over t from t1 to t2. Bam. Okay, so again, okay, the units of temperature dt and t, they cancel. So Cp is going to have my units of R. Okay, this has units of R. All right, so my units work out. My P term, I already have the negative term in there, so I just need to add this plus this. Okay, so now putting it together to get ds in units of joules per mole K. Okay, so ds then, my ideal gas, is going to be equal to my T term plus my P term. Okay, cool. Okay, and I'm just going to keep this as a script, right? Why not? Okay, and so yeah, let me just keep this as a script, and let me save as, what's this, 1311.m. So this is exercise 13.1.1. Okay, cool. All right, so now if I run it, okay, it runs, and here's my answer. So this is my change in entropy for my ideal gas, and this is in joules per mole Kelvin. Okay, great. Okay. So there's part one. All right, so let me just keep recording since we're rolling. So here's part one. Now part two, where we differ, is now my compression is going to be isentropic. So it's going to be the same problem, the same system. Okay, T1 and P1 are the same and given. Okay, but now I'm not given a value of T2. Okay, P2 is the same. So instead of compressing from some initial temperature to some final temperature, all right, now I'm going to compress isentropically. So I know T1 and P1, and I know P2, my desired final temperature. But now instead here, I'm told that ds is equal to 0. Okay, great. All right, so I want to solve for T2 for when delta S is equal to 0. Great. So let's try and do this. Okay, all of our parameters are the same except we don't need T2. So let's just give it a try and do it. So remember the strategy we did in class to try and solve a problem like this. So I'm first going to start, and I'm just going to save as, and I'm going to call this 13.1.2. Okay, so I'm going to create a copy of my script, so I'm starting fresh. Okay, and I'm going to clear all. Since I wrote a script and not a function, I'm going to make sure my workspace is clear, so I don't accidentally use some piece of information that I don't know. Okay, and what I'm going to do is all of this information is the same. Okay, but going through, what changes is now I don't know T2. Okay, so I'm going to start by commenting out T2. Right, I'm going to start by kind of taking that leap of faith. Okay, this is what I want to do, and now I'm going to need to make my code work based on this. Okay, so T2, I don't know. Okay, so I'm just going to comment it out. Okay, but I still know T1. Okay, this is the same. R's, this is the same. Here's still my constants. My pressure terms is still the same. Okay. The term I need to integrate, Cp divided by T, that's still the same. So having an anonymous function for that, still good. Okay. But now here, right, is where things are going to start to change. Okay, so the issue is on line 21, I can't compute this integral because I don't know T2. Okay, I don't know T2. Okay. I know that delta S, I'm searching for when delta S is equal to 0, but I don't know T2. Okay. All right, so what can I do? Okay, well, let's, I could, in theory, I can make this a function. So my T term, I could turn into an anonymous function. So it could be a function of T2, okay, where I'm going to integrate this term, Cp over T, from T1, which is known, to T2, right, which is my input to that function. All right, so I could take this, and I could turn this into a function. Okay, cool. And then what I could do for ds is I'm actually looking for when ds is equal to 0, right? And so if I want to solve, so now putting it all together, to get, okay, ds is in units of, now putting it all together to solve for T2 for when ds ideal gas is equal to 0, okay, well, I could do something like this. Let me do T2 is equal to, I use my friend F0, okay, and actually what I'm going to do is I'm going to take this, okay, and instead of calling this T term, I'm going to call this ds ideal gas, because ds ideal gas is just my T term, okay, then I'm going to add to it P term, okay, and so then here, all right, just to simplify it for me, I'm going to put this ds ideal gas. What's the search range? Well, here's a case where maybe let me start with an initial guess. Before T final was 500, so maybe let's just start with that as initial guess. Okay, and that should be it, right? This is, I just commented out T2. Everything else remains the same. Calculating my P terms exactly the same. The term I'm going to integrate is exactly the same. What's going to differ though now is I don't know my upper limit of my integral. So instead of calculating my T term, I'm going to turn this into an anonymous function in which I specify the value of T2 as an input. And And here I just added the p term to it to simplify it, to reduce it down to one step. And then I'll use a friend F0 to solve for the corresponding temperature, T2. All right, so I'm going to vary the value of T2 until this evaluates to 0, and I'll start with an initial guess of 500. Okay, so running, right, it converges, right, and I get a temperature of 701.9 Kelvin. Okay, and so that's all I had to change. Okay, and so solution strategy was I start by commenting out T2. I don't know what it is anymore. Then adjust my code accordingly. Everything works normal, right, until I get to this bottom part, and that's where I need to make my adjustments. Okay, but that's it. That's chapter 13. Hope that helps. If you have any questions, let me know.